So we're going to continue on with algebraic thinking and talk about the idea of a function. Function is kind of like a rule. It's an equation that we can plug into and we get one value out, so it's a given rule with no exceptions. So the rule here is the idea that one value is given to the function and it results in a unique value. So if I look at these examples and I'm looking for what is the teacher's rule, how is she coming up with these numbers? Then in A, if I look at it, every value in the teacher column is 3 times the student value. So then my rule would be 3 times n, where n is the student value. If I look in part B, this one's a lot trickier. You may not have come to this assumption on your own, and you're going to need to work on coaching your students up to this. But if I look at this, it's one off from double the number. Do you see that? So like 5 is 1, 1 above, 2 times 2, which is 4, if I double the number. So that's why it's 2n plus 1. Here, if I try and guess the teacher's rule, and I'm looking at this, well, all of my n values are even, so that's interesting, first of all. If the number is odd, it's going to be 1. So I have 2, 4 with these even numbers with a value of 0, and then the odds are causing a leftover value. So there's other answers possible here, and it's not going to be a function because we don't have unique values. So something is going on here, and it's not something that's going to be a function or a rule. So there's not going to be a rule here to find. A lot of people allude the idea of a function to a machine. You input one value, you get out something else. They do input output, and that's why they think of the idea of a machine. So here's an example of I input 4, I add 3, I get out 7. And then the function notation is the number you plug in goes in parentheses, and the letter F in front just stands for function. What you get out comes after the equal sign. So if I was to create a table based on this function rule, I'm going to put those numbers, those x values in, and I'm going to add 3 to each of them to get the right-hand column. Functions are often going to be looked at as equations. Not every equation is a function, but every function is an equation. So if I'm looking to write an equation, I have f of x equals x plus 3. If I'm inputting x values, so numbers, then I can input those into the equation to get the output values, and that's what generates the answers on the right-hand side. So we have something called a domain. A domain is all the numbers that we plug into the function, and the range is all the numbers that we get out of the function. Functions can be thought of as this input-output situation. For natural numbers x, the machine puts out a number that is less than x. So is that going to be a function machine? And this again, we're playing to the idea of a machine, but is it going to be a function is really what's in play here. So if I look at this, the answer is definitely going to be no. Because if you put in the number 10, the machine may output 9, since 9 is less than 10. But if I put it again, I might get 3, because 3 is less than 10. So there's lots of options for something less than 10. And because there are options, it's not a function. So here's an example with a high-end bicycle situation, and I'm going to read it for understanding the first time, and the second time I'm going to start pulling things out, like if it's $500, it's 500x, because I'm making X bikes per day. If the fixed cost is $1,400, I have to add that cost to the cost of making the bike. If they're selling the bikes for $700 and the profit or loss in producing and selling them is going to be given by P of X, then I want to solve that in terms of X. So when I simplify that whole idea down to I'm selling them for $700 each, so that's 700X. They cost $500 to make, 500X, but I also have to account for that 1,400. Now when I distribute the subtraction through, that 1,400 becomes negative. And that's going to be the simplified profit function. If I wanted to then take that a step further and say, well, where does he break even? I'm going to set that equal to 0 because if you break even, you're at a 0 profit. And I'm going to solve that for x by adding 1,400 to both sides and then dividing by 200. So if he sells 7 bikes, he breaks even on his cost. But if he sells more than 7 bikes, then he's doing really good there. So we have both of those scenarios available. Arrow diagrams are often used to show if we have unique values or not. So we put our domain on the left and our range on the right, and we're showing these arrows to the different values. If I have arrows that are going to one value, it's unique. But if I have arrows that are going to two different values on the right, it's not unique and it's not a function. So take a minute and look at these examples and see which ones of these can be functions. So in this case, the only one that can be a function is going to be the last one. D is left out of the range because nobody results in the output of D. So it's not actually going to be considered in the range. Here I have a function and my range would be Brown, Smith, and Doe. If I was looking for a domain, it would be John, Mike, and Joan, and Sue. Here in the second one, it is a function and the range is the different values on the right. And then this is where the bread and butter happens with algebra. I use functions in tables and ordered pairs 90% of the time. This is where we're taking these students on the journey for. We're taking them to eventually utilize these tables and these values. So here's the table and value for this lawn service. And from this table, if you notice the column on the left is going to be the first number in the parentheses. The column on the right is the second number. So I can write a table as an ordered pair, and that's a key skill. So if I look at these ordered pairs now, and I'm trying to determine if they're functions, it's a little trickier than when I have the diagrams. But I know that A is not going to be a function because when I plug in 1, when 1 is the first value, there are two different outputs in the second value of the parentheses. So if you're looking to see if it's a function, the first thing you want to check and see is if the number and the first number occurs more than once. If the first number occurs more than once, then you're going to look at, okay, are there two different or three different or four different numbers behind that first number? That's how you're going to check it. And then in B, no number occurs twice in that first slot, so it's automatically going to be a function. C is going to be a function. I can list my domain and range out really nicely as a list. And then this is also going to be a function because if I have A is going to be some value in and B is going to be 2 times A, I'm never going to be able to get the same thing if I'm doubling something. So it's going to be a function. Now, when we move from ordered pairs into graphs, that's the end product. We want them to be able to graph. The first number in the parenthesis is the horizontal axis. The second number in the parenthesis is the vertical axis. So you just plot the points. If it's 1, 50, that's going to be this point right here. Now, this is another example, but this time instead of specific moments in time, I have a range of values for the number of minutes and how much the call is going to cost. So these are called step functions because they look like a set of stairs. If the graph does not depict a function, meaning that it does not pass the vertical line test, so if I draw a vertical line right here, I'm going to see it touches more than one time, so that means that there's more than one value. It's going to not be a function. And then, for example, in this case, I could be charged either 50 or 85 cents for a 2-minute call. It could go either way. Sequences, while they're often just seen as a list of numbers, they can also be looked at as a situation of functions. For example, if I have an arithmetic sequence, I'm plugging in a term number and I'm getting out a sequence number. It shouldn't really happen that I get the same sequence number out when I'm plugging it into the equations. So they're going to give us functions. So if I'm looking at part A, an arithmetic sequence whose first term is 3 and whose difference is 3 as well, would be 3n, where n is a natural number. A geometric sequence whose first term is 3 and whose ratio is 3 would be 3 to the n, where n is a natural number. Because remember, geometric is going to be a multiplication product. Now, we have some formulas to help us find the sum. So when you're doing things in the lab, do not add up the first 100 numbers. Utilize this sum formula. So if I want to find the sum of the first 100 terms, that means that n is 100 when I'm looking back at this formula. And my starting term is 3. I have to find my 100th term. So I'm looking at, okay, to find my 100th term, I need to find the common difference. The common difference is 4. And then I'm going to plug the 4 into the term number equation to find out my term number. Once I do that, I can find out my sum is 498. The sum of a geometric series is not as pretty. It's going to involve putting that top numerator into a set of parentheses and that bottom numerator also into a set of parentheses. So if I want to find the first 10 terms of this geometric sequence, I'm going to plug it in to my formula. I'm going to take each one and divide it by the common ratio. Then I'm going to find the sum. I know my ratio is going to be 1/2. I'm going to do 1/2 to the 10 for the 10th term. And then I'm going to do 1 over 1 minus the ratio. And that's going to give me my sum. The composition of functions is where I'm composing one function and another. So it's like it passes through the machine twice because it's going through two different equations. In this case, the number 2 is entered at the top, and when I get it out of the equation x plus 4, I get 6. But then I'm putting 6 right back into the next function, and I'm getting out 12. This is called the composition of functions because it's passing through two different distinct functions. You should also notice the range of f is going to be the domain of g because you're plugging in what you get out. So composition of functions is shown with this open circle. A lot of students mistake this open circle to be multiplication. It is not multiplication. This is a composition, which means you're going to plug 3 into the g equation first. You're going to get that answer, and then you're going to plug that answer into the f equation. In the B, you're going to plug 3 into the F equation first, then you're going to get that answer and plug it into the G equation. Same thing here is true for C, but this time in C, I'm using variables because I'm taking x minus 3 and I'm plugging that into 2x plus 3. So I have to take that x and replace it with the g of x function, and then you're going to simplify it. This is another illustration of doing the opposite. So you're going to take the f equation and plug it in as x into the g equation, and that's going to simplify to 2x. A relation is what happens when something is not a function. Everything is a relation, but not everything is a function. Any set of ordered pairs is a relation. Note that every function is a relation, but not every relation is a function. So it's going to be that same idea as we saw with real numbers, and we see that overarching larger idea. So if we consider the relation as a sister of something, this idea, this big overarching idea, this figure illustrates the relation among children on a playground where I have letters A through J are going to be kids. An arrow from A to J is going to indicate a relationship. Notice the arrows that I have here indicate that F is a sister of G and G is a sister of F. So they have that reciprocal sister relationship. So that means they're both girls, if they're both sisters. On the other hand, the absence of an arrow from J to I implies that J is not going to be a sister of I. And so I then would have to be a girl and J would have to be a boy because the arrow is only going one way. Another way to show this could be that A is a sister of B as an AB, and then I can start writing out those relationships as ordered pairs. So I'm taking those arrows in, I'm looking at where A goes, and I'm putting them into ordered pair situations. So then I have that would be a subset of everybody. Given any two sets, a relation is going to be a subset of it. The reflexive property seems like it might be redundant, but the reflexive property is that something's always going to be equal itself. A is always going to be equal to A. 2 is always going to be equal to 2. The symmetric property, on the other hand, is going to involve the flipping of something. So if I have 2 equals x, that's not how we like to write things. We like to write x equals 2. So we would flip it around. The symmetric property is what allows me to make that flip happen. The transitive property is going to allow me to equate two things in a three-step process. So if I had something like A equals B, B equals C, then I know A has to be equal to C because A is the same as B. If I have an equivalence relationship, that means it's going to meet the qualifications of all three of those properties.